My name's Claudia Mack. I'm a rising senior here at Barnard. I'm from Houston, Texas. I'm majoring in environmental science and minoring in chemistry, and I spent my summer doing research under Professor Martin Stuta. He's the head of the environmental science department here at Barnard. And so I was working on a carbon sequestration project in Iceland. And Martin Stuta is also a research scientist at the Lamont Doherty Earth Observatory, which is Columbia's Earth Observatory. So I spent my summer up there researching and doing all the lab work, and then I created a poster about it. So I'll just kind of introduce what carbon sequestration is. Basically, as a lot of people know, we have this issue of global warming, so basically carbon dioxide emissions are increasing. We're emitting a lot of carbon, and the concentrations have risen past 400 parts per million. So carbon sequestration is also known as carbon capture and storage, and that's basically taking carbon dioxide out of the atmosphere and trying to store it in geological formations so that it's safe, it's not harming the environment any further. And so I was part of a project called Carb. Martin, my advisor, is very involved with that project, and it's basically a pilot scale project involving collaboration with the University of Iceland, a university in France, Reykjavik Energy, and Columbia. And so it's basically a pilot scale project trying to imitate natural carbon dioxide storage in basaltic rocks in Iceland. So first, the carbon dioxide is captured from the atmosphere. So here's the site, first of all, this map. So the carbon dioxide is captured from a power plant near Reykjavik, and then the carbon dioxide that is emitted is dissolved into water from a groundwater source over here. And then once the carbon dioxide is dissolved in that water, the water and fluids are injected into a well, HNO2, which is here. So the water is injected into that well, and then when the groundwater is moving along, it's sampled along its pathway, and then I was in charge of sampling those water samples throughout the summer. So the water samples are injected with tracers. SF6 and carbon-14 are the two main tracers used. SF6 delineates the fluid flow path so we can see where the water is moving, how fast it's moving. And then carbon-14 is a way of tagging the carbon dioxide, basically identifying the carbon dioxide we injected versus the carbon that's underground at the time. And so by taking those two measurements, we can see how the water moved and also how the water, the rocks, and the carbon dioxide interacted and what happened to it. And so here's something about the lab work I did. For the SF6 analysis, we used gas chromatography. So here's a picture of me using a gas chromatograph and just, injecting the sample. And then in this section of the poster, there's a picture of vacuum distillation. That's how we extract the carbon dioxide out of the samples and measure how much is in those samples. So we have to basically distill out the carbon dioxide with multiple stages of it, and then it's captured in a little glass rod that we flame seal at the end. So that's a picture of the flame sealing. So here's some results about what happened. Oh, I think I just stepped on the microphone. Did it mess up?
It's fine.
Okay. Okay, so here's some results of what happened in Iceland. So the tracer activity, as I mentioned, we've been monitoring very closely. So we don't have the results from the carbon-14 yet because they take a long time to process. So instead we can use dissolved inorganic carbon as a proxy for that to basically understand how much carbon's in the water. So here is when the SF6 and carbon-14 were injected. And so there's a big spike here after the initial injection. And what we see is that the SF6 concentrations continue to rise as it moves through the water, which we would expect. However, the dissolved inorganic carbon concentrations remain, after that initial spike, remain relatively constant. So what we can say about that is that because they remain relatively constant, even though we injected an additional carbon into the water, that carbon dioxide is precipitating out of the water. So what's happening is there's a reaction over here that I wrote. When the carbon dioxide is dissolved in water, it becomes carbonic acid, which then dissociates into bicarbonate and hydrogen ions, and then that further dissociates into carbonate and hydrogen ions even further. So these carbonate ions react with the metal ions in the rock in Iceland, the basaltic rock. And so basically what's happening is these carbonates are forming with out of the carbon that we injected. So basically that means that even though we injected additional carbon, that carbon is precipitating out as carbonates. So that's really exciting. Those carbonates are not harmful to the environment, so we think that's still being investigated, but we're hoping that if they keep precipitating out as carbonates, then that's basically removing carbon dioxide from the atmosphere, creating these harmless carbonates, and we solve a really big problem. So that's, those are the main parts of this project. It's a very exciting project. There's still a lot of work to be done, obviously, and there are further injections going to be occurring. There's a lot more samples coming in all the time, but the preliminary results and results we've seen in the past few years have been so far very successful. So very exciting.